yesterday. So today's lecture is likely to be somewhat short for the reason that I want to finish up to a certain point where we still use elementary tools. Once we get past that point, we have to use the theory of the Fourier transform and Plancherel theorem. So the type of analysis changes after the point we are at today. So I will like to treat that separately tomorrow. So I will keep the lecture somewhat short. Okay, that's the first thing. Now let us review what we were doing yesterday. So the point is, so we are looking only at the first part, what I've called the first part of Halash's theorem, which in fact is the longest part in the standard proof of Halasz theorem, meaning the classical proof of Halasz theorem. And that is that if you take a multiplicative function, a function from n star to c, taking complex values, but values all of absolute value less than or equal to 1, so within the unit disk, and suppose that this particular series, summation 1 minus the real part of fp times p to the minus I tau by p, this series diverges for every real number tau. Okay, so this is a series of positive terms, remember, because the real part of this is a number, it's the cosine of, it's in absolute value less than, so this is less than 1. And therefore, you see this, because your FP is less than or equal to 1. So this is a series of positive terms. This number inside is itself a complex number of absolute value less than or equal to 1. So its real part is less than 1. And therefore, 1 minus the real part is always some positive number. So this is a series of positive terms. Therefore, if it has to diverge because sigma 1 by p diverges. And that can happen only if the 1 minus real part is slightly big. Okay, and that can happen only if fp times p to the minus I tau, this is not, the cosine here is not 0. So, the angle is not 0, so that you don't have too many ones. If this has too many ones, then this will cancel out and the series will converge. So that will this divergence happens when fp is not close to p to the I tau in a way. So from this point of view, if it's not close to p to the I tau as a function, then you would expect this series to diverge. And the point is that if fp doesn't behave like the function fn, it's a, the function f doesn't behave like the function n goes to n to the I tau for any tau, then indeed it has a mean value and that mean value is 0. So this is the striking part of Halash's theorem. It tells you that except for these functions n to the power I tau for various real numbers tau, all other multiplicative functions that take values in the unit disk have actually mean 0. So there's enough cancellation to ensure that the sigma fn becomes little o of x as x goes to infinity. So this is a striking theorem, and this is the only a part of Halash's theorem. The other parts, as you know, cover the case when there is a tau for which the series converges, and then what exactly is the behavior of partial sums. So this part, however, has the longest proof, and we were looking at the first part of the proof. So yesterday, to review what we did yesterday, so we started by passing to a mean. So we said yesterday there was a print, not print, rather handwriting mistake, as in I made a slip when writing. So yesterday I had defined AX as 1 by X times sigma Fn 1 less than n less than X. But actually, as I mentioned yesterday, the 1 by X was an error. And AX should just denote the partial sum of Fn of F up to X. Okay. I just for convenience, I define this for any real number X, but plainly if X is less than 1, there are no terms to add, and therefore AX is 0. So this is a convenient, assumption. So you define AX to be 0 for X less than 1, and for X greater than or equal to 1, you set it to be equal to the corresponding partial sum. Okay, that way you get a function that's defined on the entire real line, and this is an advantage when you are looking at integrals and so on, everything. It's easy to write down things. So for any X greater than or equal to 1 and all T in 1 to 2X, yesterday we showed that for any X greater than or equal to 1 and all T in 1 to 2X, AT log T is less than or equal to the sum over all primes of AT by P log P plus X. So it's not less than or equal to. Please note that this is a standard notation in analytic number theory. It is to be read as less than if you wish. So there are two less than signs. And as I probably mentioned earlier, it means that the left-hand side is less than the expression on the right-hand side multiplied by some particular constant, which is usually absolute, but which we are not interested in. So when I say AT log T is less than this, it could be that AT log T is less than 5 times the right-hand side. But since the number 5 is not of interest to us, we omit it and simply use this notation to say it's less than some constant, which we are not bothered about what, times the right-hand side. Okay? So I do hope that is clear to most of you. At least many of you are actually doing analytic number theory and are probably familiar with this notation already. But for those who are just starting, this is an important notation to get used to, right? Now, note that in this sum, when P is larger than T, AT by P is 0, because you see AX is 0 when X is less than 1. And therefore, this sum is actually finite. But it's convenient to write this as a sum over all prime numbers so that I don't have to put some inequality on the subscript of the summation notation. It is automatically taken care of by the fact that AT by P will be 0 as soon as P exceeds T. Okay, so actually it's a finite sum. So there's no infinite sum here, but it's convenient to write it as AT log P is less than or equal to AT by P log P plus X. You see that this is what we proved yesterday, and you see it's already something remarkable in that you wanted to study AT for any T or AX for any X, and you have translated that to its behavior for certain special indices, namely X by T, where T is only a prime number. Okay, so you're adding all of them with these usual weights that you assign to primes, and this translation happens. And that's what we studied yesterday. We will, of course, review the procedure in brief in a little while. Okay. Now, note also that we have the trivial bound, which, as Lalit asked at the beginning of the lecture, we keep using the fact that the FNs are assumed to be less than or equal to 1 in absolute value. So AT is less than or equal to 1. AT is less than or equal to the number of integers up to T, which is integral part of T, which is less than T. So we'll constantly use this bound. AT in absolute value is less than or equal to T. It's the trivial bound for the partial sum. Okay. Of course, our aim is to actually show that not only is AT less than or equal to T, AT is actually less than any epsilon times T if T is sufficiently large and epsilon given any a positive number. That's what we want to show. But the trivial thing says that AT is less than or equal. Okay, therefore, AT by P log P is less than or equal to T times log P by P, and this sum you see is less than log T. And therefore, a trivial estimate, if you just use the triangle inequality on the identity that on the inequality we proved yesterday, what you will get is AT log T is less than T times log T plus X, which is a trivial assertion because AT is actually less than T, and you multiply log T and you don't even need the extra X, and you get that it is true. Okay. So one can criticize this inequality by saying, what have you gained from it? I mean, you're just making, if I apply triangle inequality to this, I get nothing. If I use the trivial estimate, I get only a trivial result. But of course, that's not the point. The point is we have to work harder to achieve something from this inequality. But what is the point? The point is that you're saying that AT log T, this function, absolute value of AT log T, is bounded by its sum over the prime number. Bounded by this sum. So you're bounding AT log T by a mean over prime numbers. Now it could be that for many primes, this value is small. AT by P is small. And therefore, AT log T itself will become small. You see? So whenever you bound a function by its own mean, you have this possibility that on the average, you see, if something is less, a function is less than its own mean, very likely that function is a constant. Because you can't be less than the mean average, the average values taken by the function itself without having, if you vary too much, right? So this is the intuition. We'll see it happening repeatedly. So now let me just go to the next. Yeah. So what were the steps in the proof of this inequality that I stated, namely the one that was stated here. So this inequality that we proved yesterday, what were the steps in the proof? First, we wrote sigma fn n less than equal to t. We multiplied it by log t. This is your AT, this sigma fn n less than equal to t. You multiply it by log t. Then you actually multiply each term. So by distributive law, you just move the log t into each term. And then when you do that, you use the n in each term to write log t as log n plus log t by n. So you have this expression, and then you get this right-hand side. As for the second sum, we just bounded it trivially. There was just nothing to do. We applied the triangle inequality and said it's less than log t by n, which is integral n to t du by u, n less than t. Interchange the integral and the sum, and you get that this is less than equal to 2x. So at any rate, it's less than x. You see, I've ignored the constant 2 here because it's not relevant to what we are doing. So the second term is easily handled and it's just disposed of like that. You simply bound it trivially and say it's less than x. So now you come to this term, fn log n, the sum over the partial sum of fn log n. And that's where the interesting arithmetical information is put in. So what do? We use the factorization of integers into primes and obtain this particular identity. So what is the identity we obtain? For any multiplicative function f and any t greater than or equal to 1, sigma fn log n is equal to this thing, fs log s times the partial sum over all integers up to t by s and summed over all s in capital S, where capital S stands for the set of prime powers, namely 2, 3, etc., 2 square, 3 square, so on, and 2 cube, 3 cube, so on. Okay, so all prime powers, right? So S is the set of all prime powers, and we showed that you take any multiplicative function, whether it's less than equal to 1 or not, it doesn't matter. This identity holds. is Fn log n is Fs log s times the sum up to of m up to T by S of Fm, minus a very similar looking term Fs log s, yes, but here the inner sum is restricted to all those integers less than T by S, which are divisible by the prime, the unique prime that divides S. Because S is a prime power, it is divisible by a single prime, namely the prime whose power it is, and Ks stands for that particular prime, and therefore you have this identity. Now, if you just, this identity is a very simple identity that comes quite easily by simply substituting log n is equal to sigma log s, where the sum is taken over all prime powers that divide n, right? So you just put it in, use multiplicativity of f and interchange summations and rearrange the terms. You basically end up with this identity, which is the starting point of a number of investigations on, the mean value of multiplicative functions. Okay, so this identity is now used together with the hypothesis that Fn is less than or equal to 1. So you use this identity together with the hypothesis that Sn is less than or equal to 1. And what do? Here you have a sum over all prime powers, and so that sum you estimate trivially the contributions from the prime powers which are not primes, so the genuine prime powers. You just estimate it trivially, and in the second sum you use the fact that the second sum, the m is only over already multiples of the prime that divides S. So you just estimate the entire sum for all S in S trivially. And then having done that, you are left only with the contribution to this sum of the actual primes, not, prime squares, prime cubes, and so on. And therefore you get sigma p in p log p Fn n by t, where the Fp that should have come here is removed by the fact that mod Fp is less than or equal to 1. And here there should be an absolute value which I have missed. So it's log p Fn n mod of Fn n less than t by p. Okay, so that gives you finally this inequality that we obtained yesterday. Now we will try to see how to, now what do we do with this inequality? So let's look at this inequality. It says that it is valid for all t in 1 to 2x, okay? So this inequality is valid for all t in 1 to 2x, right? Now we want to use this inequality to our advantage. Gosh, I don't know what's happening. What did I click? Sorry, something I clicked, I think.
It's fine, sir.
You can, is my screen okay?
Yes, sir, it's fine.
Oh, I thought something had appeared on, sorry. Okay, now we want to use this inequality, but not quite. We will actually do one more step, which is we'll average this inequality. Okay, so the actual inequality that we will finally use is an averaged form of this inequality that we have. So how do we average? So first, let us set y equal x over log x. So y is, as x goes to infinity, see y is much smaller than x. So for a given x, you look at this interval, which is of length 2x over log x. So it's of small size around x. Okay, and we take t to be any element, any real number in this interval, x minus y to x plus y. Okay, let's see how much ax log x varies from at log t for an arbitrary t in this interval. So let's look at how much the variation is. So you can just immediately write ax log x minus at log t is ax minus at log x plus at times log x minus log t. right? So this is quite a straightforward rewriting. It has nothing specifically to do with the function f or a or any such thing. It's simply the simple identity that just obtained by checking if you multiply the log x, if you cancel off, and it's just how you handle bilinear relations. So you get this. So this tells you that the difference between ax log x and at log t is given like this. Now let us estimate each term. Ax minus at is trivially bounded by, this is the difference of two partial sums, and t lies in this interval, and the interval is x minus y to x plus y. So at most this difference of partial sums is at most sigma fn in absolute value, n in I, right? And the interval has length 2y and fn is less than or equal to 1. So this difference is at most 2y. Also, t is, t is at least x minus x over log x, since y is x over log x. And that is at least x over 2, since you have assumed that x is greater than e square or something. So your log x is at least 2. So that log x minus log t is less than or equal to 2. Okay. So if you use the trivial bound for at, which is less than or equal to t, you see that this whole thing is less than 2t, the second term, and the first term is less than 2y, which is x over log x. So you conclude that ax times log x minus at log t is less than or equal to x plus 2 times x over log x, basically. So all this just gets combined into a single x up to a constant, and therefore you conclude that ax log x, I should put absolute values in principle. So absolute value of ax log x is less than absolute value of at log t plus x. Okay, for all t in this interval. For all t in this interval, you see that the variation is only at x. Okay. So now, what is the use of making such an observation? I have looked at the difference between the value of the function I want to analyze, namely ax log x, and its values in a small interval around the point I want to analyze it at. I have obtained an absolute, an upper bound for the difference in these two values. So f of x minus f of t is bounded by, in our case, this x. So I know that f of x is less than f of t plus mod f of x is less than mod f t plus x. That's the situation I am in. I want to take advantage of the fact that this is true for all t in I. Okay. For all t in I want to take advantage of this fact. So what I do is I integrate this inequality over all t in the interval I. So I multiply the characteristic function of the interval to both sides and integrate the resulting inequality and divide by the length of the interval. So all the constant terms in this inequality, namely ax log x and x, they will be unaffected by this average because they are all constant. And you have divided by the length of the interval. So you see, these things are not going to change. What will change is that at log t will be replaced by its average over the interval. I have put the characteristic function of the interval, though I have written the integral as over the real line. It's actually the integral is actually over the interval I and by the length of the interval. So it's the mean of at by t plus x. So what have we got out of doing this? We are just saying that if ax log x is less than or equal to at log t for all t in some interval, then it better be less than the mean of at log t over that interval plus x, which is completely natural and obvious. Again, by such averaging, and Professor Balasubramanian could have shown you that in fact you can do in certain situations multiple averaging and gain substantially by the process. So that is what is done in his method. Okay, but here we just average once, and you get that ax log x is less than the mean of at log t over this interval plus x. Okay, so now to apply this, now what do? Now you use the thing that we have proved, namely that at log t for any t is less than at by p log p plus x, as long as t is between 1 and x. Okay, so we use the inequality that we originally proved here after having averaged, first writing an averaging statement, average it, and then plug in this inequality inside this integral. Okay, so I put this inequality into this integral, and then I get the integral to be written. Our integral gets written like this. So the characteristic function of the interval, summation over p at by p log p 1 by y plus x, and so on. So this just comes plainly out of substituting for at log t the right hand side of this inequality, which we proved yesterday. Okay, so you don't estimate ax log x directly. You first average it by saying, okay, ax log x is less than equal to its own value at all points in an interval about x plus a small error, and then you average that inequality, and in that averaged inequality you substitute the bound that you had for at log p from yesterday. Yeah.
This is it 1 over 2 power y or just 1 over y? Left side.
1 by 2y, 2 times y. The length.
Okay. 2 times y. Okay.
It's the length of the interval I, which is x minus y to x plus y. So the length is 2y, and therefore it's 1 by 2y. That's just my handwriting there. Yeah. Okay. So you have this particular inequality now. Now I have to deal with this integral on the right hand side. To do that, it's more convenient to get rid of this t by p's and just make a change of variable, but so that I have just at here. But if I want to do that, you see the p is varying inside this summation. So first I have to interchange the sum and the integral, and that is what I will do. So I'll rewrite the integral on the right hand side. So just keep your attention on this integral alone, which we will consider for the moment. So the integral is the characteristic function of this interval I. So name here, then at by p log p dt. Okay. So let me hope that I have not missed anything. You just see that it is just this sum times the characteristic function times dt. Okay, so that is what we have here. Now you interchange the sum and this integral. There's just no issue. Everything is positive. You can interchange the sum and integral as many times as you want. So you having interchanged it, you see that each term here is the integral of at by p log p. And now you here inside this integral, p is fixed because the summation is outside. So you can freely change the variable of integration. So you can make a change of variables. T goes to pt. Okay. So if you do that, you replace t with pt. So you have p here, p dt here, and your at by p gets replaced by at, and then you get and then you have a log p, which is anywhere there. So now interchanging these things, so you take your, again interchanging the integral and the sum, the integral goes out and the sum goes in. And what you finally have is just p log p, the characteristic function of the interval evaluated at pt dt. And the integral is of absolute value at times this particular sum over primes dt. Okay. And note that this integral is at is anyway 0. At is anyway 0 when t is less than 1. So in principle, this integral is just 1 to infinity of this thing. So the actual range of integration is just 1 to infinity. But for convenience, it's convenient to just write integral over R. Okay? Therefore, we have got, if you combine with the original inequality that we had, namely, if you combine with this inequality, the change of variable that we did, we finally end up with mod ax log x is less than 1 by y, integral mod at, this sum dt coming from here, plus x. Okay? And recall that y is x over log x, z is x over log. Now we introduce this new symbol z for x over log x whole square. I mean x over log x the square. Okay? So y already was set to be x over log x. So z is less than y, of course, and indeed it's x over log x square. Now I look at this integral and I want to estimate the contribution to this integral from, so t goes from 1 to infinity in this integral. Okay, that's the range of integration from 1 to infinity. So I break this integral into two parts, those t which are less than equal to the z that I have put here, and those t which are greater than equal to this. Okay, so you have two parts to this integral which I will estimate separately. So first the contribution from the t's that are greater than equal to z, and then the contributions from the t's that are less than or equal to z, where z is x over log x. Okay, so next, let's try to see the contribution from t greater than or equal to z. Just check. Yeah. So the contribution from t greater than or equal to z, the integral is z to infinity at sigma p log p chi I dt. Okay. This is the, excuse me, I don't know why this. Okay, so the contribution from t greater than or equal to z. So it's at p log p chi pt dt. Okay, so you put that, you interchange the sum and the integral here, you get p log p integral z to infinity at chi I pt. So this is the contribution from t greater than or equal to z. Now I is this interval x minus y to x plus y. Okay. Therefore, this integral is going to be 0 if this characteristic function here is going to be 0. And it will be 0 if p times t exceeds x plus y. But t is greater than z. So if p times z already exceeds x plus y, then necessarily this characteristic function will just be 0 for all such t, for all t in z to infinity. Therefore, this outer sum is restricted to only those primes which are less than or equal to x plus y by z. For a prime that is greater than x plus y by z, the integral here corresponding to that particular prime p will be 0, because p times t for any t greater than z will of course be outside the interval I, and the characteristic function will read 0. Okay? So your primes here are now restricted to x plus y by z. Therefore, your sum here is p less than equal to x plus y by z. Now the interval I is x minus y to x plus y, and pt lies in this interval, and therefore p lies between x minus y, t lies between x minus y by p and x plus y by p, because pt lies in this interval. So this integral is actually x minus y by p to x plus y by p. And for at, we use the trivial estimate at is less than or equal to t. And therefore, if you integrate this thing, you're going to get x plus y by p whole square minus x minus y by p whole square. That is using a square minus b square being a minus b, a plus b. You get xy basically up to a constant. Okay? Because you get the difference of the two, which is 2y, and the sum of the two, which will be 2x. And therefore you get 4xy by p square, and that will be multiplied by p log p. You cancel one p and you get the sum of log p by p for p up to x. And this sum is bounded by log of x plus y by z, because p is up to x plus y by z. So you get xy log x plus y by z, but z is x by log x square and y is less than x. So this is less than log of 2x by z, which after you put in the z, you get xy log x. So the contribution to this integral from all t greater than equal to z is trivially estimated, and it's just xy log x. There's just nothing here. You simply use the trivial estimate for at, and therefore for large values of t, there is nothing serious in estimating this integral. It's easily done, and it's bounded by xy log x. Okay. Now, what about the smaller values of t? There again, the thing is relatively easy, except that you have to use a hard theorem. I mean, a deep theorem, deep but useful, very elegant theorem. So the contribution from t less than z. Okay. So here you have integral 1 to z mod at sigma p, the primes, the sum over all p in p of p log p chi I p t t. Again, this condition tells you that p is between x minus y by t and x plus y by t, and you are interested in this sum. Now, this sum is p log p is not a serious obstacle. You just bound it by its maximum value on this interval. So it's x plus y by t times log of x plus y by t. And then you have to multiply this by the number of prime numbers in this interval x minus y by t to x plus y by t. The length of this interval is 2y by t, as you see. And t is this time less than z. And therefore, the length of the interval is 2y by z, at least 2y by z, which is 2 times log x, and x is greater than e square. So this is greater than 4. Okay, since x is greater. So this interval is of length at least 4. Okay, that's one good thing. It's very trivial, but small point to check. Okay. Therefore, I have to count the number of prime numbers in an interval of length xy, of length 2y by t. And I need to have a method for doing this. Now, you might say apply the prime number theorem, to up to the both endpoints of this interval and then subtract. The trouble with doing such things is that when the length of the interval in principle can be very short, the error terms in the prime number theorem will swallow up any estimate that you have when you subtract. So you actually need, to get an upper bound for the number of primes in a short interval is not an obvious, not a problem that you can solve so easily unless you have strong information on the distribution of zeros of the Riemann zeta function, which we don't have at the moment. Therefore, alternate methods were developed to get such upper bound, and the topic of sieve methods deals with this sort of problem. And one of the very nice results within the topic of sieve methods is an upper bound. Remember, it's an upper bound for the number of primes in a short interval, and that is given by a theorem called, there's a spelling mistake here, CH, Titch, which will be T-I-T-C-H-M-A-R-S-H. The Brun-Titmarsh theorem gives you an upper bound for the number of primes in an interval of form m to m plus n when n is greater than or equal to 2. This number, the number of primes, is less than twice the expected sort of thing, which is 2 times n. So the bound is 2n by log. Okay. This form of Brun-Titmarsh, which is so elegant, is actually due to Montgomery and Vaughan. It's in
Surya, maybe here it's 2 plus epsilon times n.
No, it's 2n log n. No, this is the large C thing.
Okay.
Anyway, up to some constant times n by log n is all that you need. Okay, so you need this upper bound, and yeah, so therefore you get 4y by t. So if you use this upper bound for the number of primes in this interval, you get x plus y by t times log of x plus y by t times 4y by t, which is the length of twice the length of the interval, divided by log 2y by t. Instead of 2, if you had any constant, it wouldn't matter. You would just get twice that constant here. And this is the bound you get. Now, rewriting that, you see that it is x plus y by x plus y times y by t square, log x plus y by t divided by log 2y by t. Now, the way we have chosen these parameters, t is less than z in any case, and z is chosen as x over log x square. So you can see that this whole fraction here, just by the choices we made, is less than or equal to 3. So the entire thing is less than, let's say, x plus y is less than 2x, y is x over log x. So the whole thing at any rate is less than xy by t square. Okay, so the estimate for this sum, p log p, pt in I, which comes in here, this sum is xy over t square up to a constant. So for t between 1 and z, this is the estimate. And now you put that in, and you get that the integral from 1 to z, at p, the sum over p, p log p chi pt, is less than up to a constant xy 1 to z at by t square dt. Okay. Therefore, if you combine everything, you recall that this was the inequality we started with, and we were estimating the contributions from this integral in the range 1 to z and z to infinity. And therefore, if you put in those contributions, and remember that you have to divide by a y, you see that you get the contribution from t greater than z is xy log x, and you divide by y and you get x log x. And this contribution here is xy by t square. T square goes into the integral. You divide by y and you get x times 1 to z at by t square dt x log x. And therefore, you have this integral from 1 to z, but this is a positive function and z is less than x. So we just extend it to x, the range of integration. And finally, if you combine, with this extra x that is there, you end up with ax log x is less than x times 1 to x mod at by t square dt plus x log x. Okay. Now you see, and this is exactly what we wanted to prove. This was the goal that we wanted to reach, at least in the first part of the proof. This is the goal that we wanted to reach. And now we have to pause and look for a moment at what we have achieved. If you divide this entire relation by x, you will get ax by x. If you divide it by x over log x, you get ax by x, 1 by log x times integral 1 to x at by t square dt. And here this x will go away, this x will go away after division by x, and you get here a 1 by log x in the first term. So 1 by log x times integral 1 to x at by t square dt plus log x by log x. That will be an upper bound for at by ax by x. And ax by x is the fraction which we want to study as it goes to infinity. So ax by x as limit as x tends to infinity, we want to show that it exists and that the limit is actually 0. Okay. What have we achieved? What we have said, got finally from here is that the fraction we want to bound is bounded by its own mean. So the problem of showing that ax by x goes to 0 as x goes to infinity is now translate it to a problem of showing that its mean on this interval 1 to x weighted by 1 by t square, this mean actually goes to 0 as x goes to infinity. Okay, so you have changed what you have achieved by obtaining this inequality is to show that the function whose behavior you want to study, you have translated from that question to studying the mean behavior of the function over an interval. Now, in the next stage, what we will see is we will use the theory of the Fourier transform to analyze this integral on the right-hand side. So that's the other key component of Halasz's, the proof of Halasz's theorem, which I will start tomorrow simply because I will have to introduce the Fourier transform.
Sir, there was a question in the chat.
Somebody can tell me how to see this chat.
Question is that where did the log term come from?
Yeah,
X log X.
I will give you that. Just please wait for a minute. I will show you the log X. I had shown it to you before, but obviously these sort of things, since the slides move faster than you can keep track of, it's obvious. So anyway, first let me just emphasize where we have reached, which is this inequality. And tomorrow we will use the Fourier transform. Tomorrow and day after, we will use the Fourier transform to analyze this right-hand side. And that's how we will conclude the proof of Halasz's theorem. The first part, then the second part is still there and so on. Okay, so now where did we get this log x from? So the log x comes from the fact that your estimate here was xy log of x plus y by z, which is an upper bound for this. And x is greater than y, so you get 2x by z, and z is chosen as x by log x whole square. So you see that x plus y by z is actually log x the whole square, and its log is 2 times log x up to constants, and therefore you get xy log x. I hope this answer is satisfactory. I missed that.
Yes, I think.
So that's the deal, right? So today, as I already said at the beginning, I will stop here, which is somewhat earlier than planned. So I will stop here because I need to speak about the Fourier transform and its properties to be used to analyze the integral of the right-hand side, which I'll start with tomorrow. Of course, we'll tweak this a little more. This inequality we will rewrite in a slightly better form. First of all, we need to replace the AT by AT, as you know, as you will recall, is the partial sum of Fn up to T. We'll put back the weight log n into this. That makes it convenient to deal with. So that will be the first step. We will rewrite this with AT replaced by AT, which is sigma Fn, replaced by sigma Fn log n, which we easily do because we know how to go from sigma Fn to sigma Fn log n. That was the first thing we proved. And then using that in this, we get an inequality. Huh?
Yeah,
Huh?
more than
Excuse me?
Okay, Surya,
Ah.
I think 2 is okay, I think. You don't need 2 plus epsilon, probably. In brute it must.
No, you don't need, sir. That's the Montgomery one. Yeah, but it doesn't matter. I mean, it's not.
It doesn't matter.
As Shankar was saying, 2 plus epsilon 3, anything greater than 2 is, any constant is fine.
Exactly.
Yeah, except that if you claim the constant less than 2, in this
That is different.
It won't matter. But you will get a Fields medal on the side.
Sorry?
In this problem, it won't matter even if you use constant less than 2, but you will be getting a Fields medal on the side. That's all. Yeah, therefore, this is where I wish to stop. Do you have any questions? Anybody has any questions, please?
Yeah. If anybody has any question, please ask.
And especially, please let me know if you are able to follow all the calculations. I may be going too slow or too fast. I don't know. So
No,
unless
sir, speed is okay, sir.
speed is okay. So because I cannot see the reaction of anybody, right? So it's a little hard to guess.
Yes, sir, that's problem with online lectures.
Yeah, it's a little hard to guess whether people are following it or it's too boring or what, you know, it's a little hard to guess.
Hello, sir. This is Mithun. Sir, this ax time log x is this bounded by this mean, then x log x. So, is there is this optimal? Like this log x is optimal?
It doesn't matter because you see that. I tell you, just 1 minute. See,
Okay.
you are going to divide by this log x.
Yes.
Finally, you're interested in the behavior of ax.
Right. So it is like log x by log.
Ax by x.
Yes.
So when you divide, you have to divide this entire inequality by x over log x, x times log x.
Yes.
When
Yes.
you divide this inequality by x times log x, what you're going to get here is log x by log x.
Right. Correct.
And then you're going to let x go to infinity.
Yeah, I mean this is fine, but as a mean value, so one can get some say quantitative version like error term, keep it error term. So in this case, the error term is like log x log o.
No, not. You see, it is. This is good enough for that purpose. It's only a trivial estimate. You will see. I mean, if you recall how we got it, it is just by a trivial estimate that this log.
Exactly.
So if you want to improve it, you can. But it is no point because you're going to finally show that this quantity, the integral divided by log x, you're not even going to get a quantitative estimate, at least in this proof. There are, I mean, I'm not speaking of the known proofs that have been researched very recently, and so, but in this proof, you are only going to show that after you divide this integral by this integral rather by log x and let it go to infinity, it goes to 0.
Yes.
That's all you're going to show. You're not even going to be able to get a quantitative, manner in which it goes to 0. In that case, improving this log x to anything better won't make any difference. You see?
Yeah, yes.
Because
Sir.
log x by log x goes to 0. That is done. And for the main term, we are only able to show that it is little of log x. So then improving the log x doesn't really make any difference. And that is what I want to say. Yeah.
Thank you, sir.
Yeah. Anybody else? Say?
Any more questions or comments? If not, thanks Professor Surya for his wonderful lecture.
1 minute, I am not able to see. Okay, so I'll get going.